Now the question is solve mod of 2x minus 1 equals 3 times greatest negative function of x plus 2 times fractional part of x. Now we have modulus function, greatest negative function and fractional part function. So what I'll do is I'll start with modulus function. I'll take two separate cases. Case 1 when 2x minus 1 is positive, and the second case when 2x minus 1 is negative. So for the first case, I know value of x should be greater than or equal to 1 by 2. So when x is greater than or equal to 1 by 2, this expression is positive, and when x is positive, mod x is simply x. So I'll write it as 2x minus 1, and this is 3 times greater function of x plus 2 times fractional part of x. So now I'll change this x back to greatest integer and fractional part. So I'll write 2 times greatest integer function of x plus 2 times fractional part of x minus 1 is 3 times greatest integer function of x plus 2 times fractional part of x. So if I'll cancel it, I'll get this value as greatest integer function of x, it should be minus 1. So that is the value of x should lie between minus 1 and 0. But these values of x, they do not lie in this interval. So there is nothing common with the given condition. So in this case, there will be no solution. So from the first case, the answer I'll get is x belongs to 5. Now, what about the second case? From the second case, when I know when the value of x is less than 1 by 2, in that case, when x is negative, mod x is minus x. So I'll write minus 2x minus 1 is equal to 3 times greatest integer function of 2 times fractional part of x. So again, I'll change x. So I'll write minus 2 greatest function of x fraction part of x plus 1, and this is 3 times greatest integer function of x plus 2 times fraction part of x. So now I'll take fraction part of x. So I'll write 4 times fraction part of x is 1 minus 5 times greatest integer function of x, that is fraction part of x is 1 minus 5 greatest integer function of x divided by 4. Now again, we know this function is restricted, its value will lie between 0 and 1. So 1 minus 5 greatest integer function of x by 4 will lie between 0 and 1. So it will be 0, 1 minus 5 greatest integer function of x, and then 4. If I'll subtract 1, minus 1, minus 5 greatest integer function of x, and there will be 3 if I'll multiply it by minus 3. So minus 1, I'll get minus 3 is less than 5 greater function of x is less than or equal to 1 divided by 5. So minus 3 by 5 is less than greatest integer function of x is less than 1 by 5. So the only integral value possible in this case is the value of greatest integer function of x, it should be 0. Now if I'll put the value of greatest integer function of x as 0, I'll get the value of fractional part of x as 1 by 4. So the value of x is 0 plus 1 by 4, that is 1 by 4. Now 1 by 4, it lies in the interval. So the only answer possible in this case is x equals 1 by 4. This is how we'll solve such questions. The question is, we need to find number of solution of the equation x square minus 3x plus greatest integer function of x when the value of x lies between 0 and 3. Now there are two ways of solving this question. Now one method is, I'll take 3 separate intervals. Case 1, when the value of x lies between 0 and 1. So when x lies between 0 and 1, what you know is greatest integer function of x will be 0. So I'll put it 0. So I'll get x square minus 3x equals to 0. So I'll get the value of x as either 0 or I'll get the value of x as 3. Now 3 doesn't lie in this interval. So the only value that I'll choose from here is x equals to 0. Now second case, when the value of x lies between 1 and 2. So when value of x lies between 1 and 2, the value of greatest integer function is simply 1. So if I'll put this value, I'll get x square minus 3x plus 1 equals to 0. So the value of x I'll get is 3 plus minus under root of 9 minus 4 by 2. So there will be 3 plus minus under root 5 by 2. So the values of x will be either x is 3 minus under root 5 by 2 or x is 3 plus under root 5 by 2. Now root 5 is 2.2 something. So 3 minus 2.2 something will be 0.7 something. 0.7 something divided by 2, 0.35. So which is less than 1. So it doesn't lie in this interval. and 3 plus root 5 by 2. So there'll be 5 divided by 2. So there'll be greater than 5 point something should be greater than 2.5. So in this case, this also, it doesn't lie in this interval. So there'll be no solution in this given interval. Now the third interval is when the value of x lies between 2 and 3. So in that case, the greatest function of x will be simply 2. So if I'll put it in the equation, I'll get it as x square minus 3x plus 2 equals to 0. So from here, I'll say the value of x is either 1 or the value of x is 2. Now 1, it doesn't lie in the solution. So I'll choose only one solution, and that is x equals to 2. And finally, when the value of x is 3, so when the value of x is 3, if I'll put it, I'll get what? 9 minus 9 plus 3 is equal to 0, which is 3 is equal to 0, which is not true. So the only solution possible in this case is either the value of x is 0 or the value of x is 2. So there are two solutions possible in this case. Now another way of solving the same question can be using graphs. So what I'll do is I'll draw the two graphs. I'll write it as greatest integer function of x, and this is 3x minus x square. So I'll draw the graph of greatest integer function of x, and I'll draw the graph of y equals 3x minus x square. So first I'll draw this graph. So it's a parabola opening downwards, a roots at 0 and 3. So its vertex is at 1, 2, and then 9 by 4, there'll be 2 point something. So that is the graph of y equals 3x minus x square. Now I'll draw the graph of greatest integer function of x. So this is 0. Between 1 and 2 will be 1. And between 2 and 3 will be simply 2. So at 3, this value will be simply 3. So these two graphs, they intersect at 2 points. And one of the point is x equal to 0 and the other point is x equals to 2. So there are two solutions to this equation. Let us take up another question. The question is, find the total number of solutions of the equation greatest integer function of sin x plus cos x should be 0. And we have to find number of solutions when x belongs to 0 to 100 pi, where this box represents greatest integer function. Now what I know is, I know any greatest integer function is nothing but an integer. So that means this cos x, it should also be an integer. So now sin x, the value of sin x lies between minus 1 and plus 1. So greatest integer function of sin x, there are only three integral values possible. So either its value will be minus 1, or it will be 0, or it will simply be plus 1. It will be minus 1 when the value of sin x lies between minus 1 and 0. It will be 0. When sin x lies between 0 and 1, and it will be 1 when the value of sin x will be 1. So for this equation to have a solution, I should have a condition where sin x and cos x, they should cancel each other. So in this case, if sin x is minus 1, in that case, the value of cos x should be plus 1. If greater function of sin x is 0, cos x is 0, and if greatest integer function of sin x is 1, in that case, the value of cos x, it should be minus 1. So what I'll do is, I'll try and find the solution to this equation in one fundamental period, which is from 0 to 2 pi. From 0 to 2 pi, cos 0 is 1 when x is either 0 or when x is 2 pi. But when x is 0 or when x is 2 pi, the value of sin x is simply 0. It is not minus 1. So this case, there will be no solution. Now what if cos x is 0? Now cos x is 0 when x is either pi by 2 or 3 pi by 2. So at pi by 2, the value of sin x is 1. Greatest function of sin x in that case will be plus 1. And minus 3 pi by 2, there will be minus 1. So in that case, it will be minus 1. So when cos x is 0, sin x cannot be 0. It will be either plus 1 or minus 1. Now for the third case, when the value of cos x is minus 1, which is when x is equal to pi. So when x is equal to pi, sin pi will be 0. So again, I'll get this as 0. So in each of the three cases, I'm not getting any solution. So there will be no solution to this equation. So answer to this question is no solution. So total number of solutions in this interval of this equation will be simply 0. So let us take up another question, which is find the sum of positive integral values of a where a belongs to 1 to 500, for which the equation, now it is greatest integral function of x cube plus x minus a equals to 0 has a solution. Now we know that this greater function, it is integer. Now this a, it is given, it is a positive integer. So clearly from this I can say this x is an integer. Now when x is an integer, then x cube should also be an integer. And when x cube is an integer, I know that greatest integral function of x cube will simply be x cube. So I can write this equation as x cube plus x minus a is equal to 0, or the value of a should be x cube plus x. Now being a cubic equation in x, it will have, so being a cubic equation in x, it will always have at least one real solution. So that means now I need to see what is the range of a that we can put in this equation so that the value of a lies in the given range from 1 to 500. Now we know that x is an integer, right? So the integral values of x that I can put is, I can put x as 1, 2, I cannot put 0, because if I put 0 then I'll get the value of a as 0, which is not in the given range. So 1, 2, 3, and then I'll put 7. So at 7 again will be less than 500. Now if I'll put x as 8, so this value will be greater than 500. So I can put the values of x starting from 1 to 7. So what are the possible values of a? So one of the possible value of a is when I'll put x as 1, another value is when I'll put x as 2, another value is when I'll put x as 7. So sum of all possible values of a is simply summation x varies from 1 to 7 x cube plus x. So that is summation x cube plus summation x. Now summation x cube is n plus 1 by 2 whole square, and summation x is n plus 1 by 2. So it is 7, and there will be 4, 7 into 4 whole square, and there will be 7 into 4. 812. So the sum of all positive integral values of a is 812. So now the question is greatest integral function of x plus greater function of 2x is less than 3. Now what I know is greater function of x plus n is greatest integral function of x plus n, and n in this case is 2x, and will be less than 3. Now here again I have a problem because it is greatest integral function of x and greatest integral function of 2x. So what I'll do is, again I'll say let x lies between n and n plus 1. So in that case again 2x will lie between 2n and 2n plus 2. So again I'll take two separate cases. Case 1, when 2x lies between 2n and 2n plus 1, and the second case when 2x lies between 2n plus 1 and 2n plus 2. For the first case I can write, now greater function of x will be simply n, and greatest function of 2x will be simply 2n. 2n is less than 3, so I'll get n is less than 1. So from here the condition I'll get is greatest integral function of x should be less than 1. Now when greater function of x is less than 1, then the result I'll get is the value of x should be less than 1. Now for the second case, what I'll do is, again if I'll write, so greater function of x will be simply n, greatest function of 2x will be 2n plus 1, and this value should be less than 3. So I'll get this value as 3n is less than 2, n is less than 2 by 3. Now when n is less than 2 by 3, so the possible integral value of n will be 0. So n should be less than or equal to 0, that is greatest integral function of x should be less than or equal to 0. So again from here I get the value of x should be less than 1. So from both the cases the only solution that I'm getting is the value of x should lie between minus infinite and 1. Now we need to solve this inequality, which is 2 minus x greatest integral function plus 2 into greatest integral function of x minus 1, and this is greater than or equal to 0, where this box represents greatest integral function. Now I know that greater function of x plus n is greater function of x plus n, so I can write it as 2 plus greatest integral function of minus x plus 2 times greatest integer function of x and then minus 2, it should be greater than or equal to 0. So I'll cancel 2 with 2. So I'll write minus greater function of x plus 2 into greater function of x, it should be greater than or equal to 0. Now I have both greater function of x and greatest integer function of minus x. So what I know is greater function of x plus greatest integer function of minus x, it is 0 when x is an integer and it is minus 1 when x is not an integer. So I'll take two separate cases. Case 1, when my x is an integer, and the second case when x is not an integer. When x is an integer, then I know the greatest integer function of minus x will simply be minus x and greater function of x will simply be x. So here I'll write minus x plus 2x and it should be greater than or equal to 0. So from here I'll write x should be greater than or equal to 0. So that is, I'll get all the integral values which are 0 or greater than 0. So the value of x here will be 0, 1, 2 and it goes up to infinite. So in this case, x is actually set of whole numbers. Now when x is not an integer, what I know is I can write greatest integer function of minus x as minus 1 minus greatest integer function of x. So if I'll substitute, I'll write minus 1 minus greatest integer function of x plus 2 times greatest integer function of x should be greater than or equal to 0. So greatest integer function of x is greater than or equal to 1. Now in inequalities, we already know greatest integer function of x greater than 1 is nothing but x is greater than or equal to 1. So answer to this question is either the x should be a whole number or the value of x should be greater than or equal to 1. So I can say final answer will be x is either 0 or any number which lies from 1 to infinite, because if it is not an integer, it is included here and all the integral points, they are included here from 1 to infinite. So it will be 0 union 1 to infinite. So now the question is, for any natural number n, prove that n plus 1 by 2 greatest integer function plus greater function of n plus 2 by 4, n plus 4 by 8, n plus 8 by 16, and it will go on and it will go up to infinite, and this value is equal to n. Now in order to prove this result, I need to prove a separate result, and which is I can write greatest integer function of x as greatest integer function of x by 2 and plus x plus 1 by 2. So this is the result that I'll need to prove first in order to solve this equation. Now what I'll do is I'll let this x as some 2k plus f, where the value of f lies between 0 and 1. So if I write greatest integer function of x, so greatest integer function of x will simply be 2 into k, where this k is an integer. Now what about greatest integer function of x by 2? So if I write x by 2, I can simply write it as this is k plus f by 2. Now k is an integer and this value f by 2 again will lie between 0 and 1. So its integral part will be simply k. Now what about x plus 1 by 2? So for x plus 1 by 2, I can write it as, so this is 2k plus f plus 1 divided by 2. So I'll write it as k plus f plus 1 by 2. Now f, it lies between 0 and 1. So if I'll add 1 to it, so I can write 1 and this is f plus 1 and this is 2. If I divide by 2, I'll write 1 by 2 f plus 1 by 2 and this is less than 1. So this value again lies between 1 by 2 and 1. So therefore again its greatest integer function will be k. So if I'll add them, so x by 2 plus x plus 1 by 2, so there'll be simply k plus k, that is 2k, and 2k is also same as greatest integer function of x. So I know that any greater function of x, I can write it as greatest integer function of x by 2 plus greatest integer function of x plus 1 by 2. Now we'll come back to our question. Now for any natural number n, I can write it as greatest integer function of n, and using this property, I'll write this one first. So I'll write n plus 1 by 2 and plus n by 2. Now I'll use the same property again for this one. So I can write it as, so this is n plus 1 by 2 and this is n by 2 plus 1 by 2 and then n by 2 upon 2. So I'll write it as, so this is n plus 1 by 2 and this is n plus 2 by 4 and this is simply n by 4. Now again I'll use the property for this one. So again I can write it as, so this is n plus 1 by 2, it is n plus 2 by 4 and then again here it is x. So again I'll write x plus 1 by 2 and x by 2. So I'll write n by 4 plus 1 by 2 and plus n by 8. So here will be n plus 1 by 2, n plus 2 by 4, n plus 4 by 8 and that's how it'll continue. So this is how we can prove that n plus 1 by 2, n plus 2 by 4, n plus 4 by 8 and this series continues up to infinite and this value is equal to any given natural number n. Now the question is, if the set of real values of x for the equation greatest in the function of 3 upon x plus greatest in the function of 4 upon x is 5 is a comma b upon c, where a, b, c are natural numbers and b and c it is expressed in its lowest form, then I need to find the value of a plus b plus c plus a, b, c. Now I clearly know that x cannot be less than 0 because if x is negative then this value will be negative and this value will also be negative. So sum of two negative numbers cannot be a positive number. So clearly value of x should be greater than 0. Now both these values, they are integral values. So if I look at these conditions, so then the condition that I should get is, so there can be three possible conditions. First condition can be, suppose when the value of 3 by x is 0 and at the same time the value of 4 upon x is 5, or it could be when the value of 3 upon x is 1 and value of 4 upon x is 4, and the third condition can be when the value of 3 upon x is 2 and the value of 4 upon x is simply 3. So these are the three possible conditions. Now beyond that, if I take 3 upon x as 3 and 4 upon x as 2, it is not possible because value of greatest function of 4 by x should always be greater than value of greater function of 3 by x. Now I look at the first case. Now for the first case, I know that if 3 upon x is equal to 0, then its value should lie between 0 and 1. So if I'll take the reciprocal, so then I'll get x upon 3 should be greater than 1. So that is, the value of x should be greater than 3. Now for the second one, so when this value is equal to 5, so that means 4 upon x should lie between 5 and 6. So this is 1 upon 5 is less than equal to x upon 4 is less than 1 by 6. If I'll multiply it by 4, I'll get 2 by 3 is less than x is less than 4 by 5. Now here the condition should be x is greater than 3 and here x should be less than 4 by 5. So there is no solution which is common to both. So from this one I'll get no solution. So the first case, it is not possible. Now what about the second case? For the second case, I know that this 3 upon x should lie between 1 and 2 if I'll take reciprocal. So if I'll multiply it by 3, I'll get 3 is greater than x is greater than 3 by 2. So here the condition will be the value of x should lie between 3 by 2 and 3. And for the second one, here it should be 4 upon x should lie between 4 and 5 if I'll take reciprocal. So 1 upon 4 is greater than x upon 4 is greater than 1 upon 5. If I'll multiply, I'll get 4 upon 5 is less than x is less than equal to 1. So now this value is always greater than 3 by 2 and this value is always less than 1. So again, there is no value of x which is common to both the solutions. For the second one also, I'm not getting any solution. Now what about the third part? For the third part, the value of 3 upon x should lie between 2 and 3. So if I'll take reciprocal, so there will be 1 by 2 x upon 3 and that should be 1 by 3. If I'll multiply 3, I'll get 3 by 2 is less than equal to x, greater than equal to x is less than 1. And for 4 upon x, I'll get the value of 4 upon x should be greater than 3 but less than 4, if I'll take reciprocal, 1 upon 3 is greater than x upon 4 is greater than 1 upon 4. If I'll multiply 4, so this is 4 by 3 is greater than x is greater than 1. So now I'll take the intersection of these two conditions. So the first condition is x should be 1 greater than 1 but less than 3 by 2. And the second condition is x should be greater than 1 but less than 4 by 3. 4 by 3. So from here I can say the value of x, so the interval which is common to both is from 1 to 4 by 3. So here the value of x will be from 1 to 4 by 3, 1 not included and 4 by 3 included. So value of a is 1, value of b is 4 and value of c is 3. So if I'll put the value of a, b and c, I'll write it as 1 plus 4 plus 3 and then there will be 12. So answer is simply 20. So now the question is limit x tends to 0, x square plus x into greatest integer function of 1 by x, where this box represents greatest integer function. Now what I know is any greatest integer function of x is always less than or equal to x but greater than x minus 1. So I can write the greatest integer function of 1 by x will be less than or equal to 1 by x and it is always greater than 1 by x minus 1. So I can write it as 1 minus x upon x is less than greatest integer function of 1 upon x is less than or equal to 1 by x. Now I'll multiply it with x square plus x. So x square plus x into 1 minus x upon x square plus x into greatest integer function of 1 upon x and x square plus x upon x. So here I'll cancel x, so I'll write 1 plus x into 1 minus x square plus x into greatest integer function of 1 upon x and this is x plus 1. Now I'll take limits. So I'll take limit x tends to 0 for all the three expressions. Now if I put the value of x as 0, I'll get this first limit as 1. If I put x as 0 also, I'll get this limit as 1. Now the sandwich theorem or squeeze play theorem say that if these two limits they are equal, then we can say that limit x tends to 0, x square plus x into greatest integer function of 1 upon x will also be 1. So answer to this question is simply 1. Now the question is solve this limit x tends to infinite log x to the power n minus greatest integer function of x upon greatest integer function of x. So I can write this, so I can take this power out. So I'll write limit x tends to infinite. So this is n ln n upon greatest integer function of x and then minus y. So now I'll solve this limit. So what I know is greatest integer function of x is always less than or equal to x and it is always greater than x minus 1. So if I'll take the reciprocal, I can write it as 1 upon greatest integer function of x will always be greater than 1 by x and will always be less than 1 upon x minus 1. Now I'll multiply it with ln x. So ln x upon x minus 1 is greater than ln x upon greatest integer function of x and this is ln x upon x. I'll also multiply it with n. Now I'll take limit x tends to infinite. Now this is log infinite is infinite and here also x is infinite, so it is infinity upon infinity form here and here also it is infinity upon infinity form. So I'll use L'Hospital rule. So I'll write limit x tends to infinite and I'll differentiate. So I'll get n. So this is 1 upon x and this is 1 and here it will be limit x tends to infinite n ln x upon greatest integer function of x and this is greater than limit x tends to infinite. So it will be n 1 upon x and then again it will be 1. So if I put the value of x as infinite, so this limit will be 0 and this limit it will also be 0. So from here I can say the value of this limit x tends to infinite n ln x upon greatest integer function of x. So value of this limit is 0. So if I put the value of this limit 0 here, so answer to this question will simply be minus 1. So limit x tends to infinite, log x to the power n minus greatest linear function of x upon x is simply minus 1. So this is how we solve these questions. So now the question is solve the inequality x into greatest function of x minus x square minus 3 greatest linear function of x plus 3x is greater than 0. So what I'll do is I'll take x common. So if I take x common, I can write greatest linear function of x minus x, and here I'll take minus 3 common. So I can write greatest linear function of x minus x is greater than 0. Now what I know is x is greatest linear function of x plus fractional part of x. So that is greatest linear function of x minus x is nothing but minus fractional part of x. So it'll be x into minus fractional part of x and then minus 3 into minus fraction part of x, and it should be greater than 0. So I'll take fraction part of x common. So here I'll get 3 minus x should be greater than 0. Now I know that this fraction part of x, its value will always lie between 0 and 1. So its sign doesn't change. So I'll remove this expression from the inequality. So the only result I'll get is 3 minus x should be greater than 0. That is, x should be less than 3. So there is one more condition, and that is the roots of the expression which we have removed from the inequality, they should be excluded from the solution if they are included there. So that means here fraction part of x should not be 0. So simply x should not be an integer. So answer to this question will be x belongs to minus infinite to 3 except all the integers which are there in this given interval. So now the question is, if the equation a minus 2 and x minus greater function of x whole square plus 2 into x minus greater function of x plus a square is equal to 0, where this box represents greatest linear function, it says if it has exactly one solution in the interval 2, 3, then find all the possible values of a. Now what I know is this x minus greater function of x is actually nothing but fractional part of x. So I can write it as a minus 2 fractional part of x whole square plus 2 fractional part of x and then plus a square is equal to 0, and this equation should have exactly one solution in 2, 3. But what I do know is any fractional part function, it's a periodic function. So if it has exactly one solution in 2, 3, so I can also say that a minus 2 fraction part of x square plus 2 times x square plus a is equal to 0 will also have exactly one solution in the interval 0, 1 also, because it's a periodic function. Its graph and its solution repeats in every 1 unit interval. So I can say this equation should have exactly one solution in the interval 0, 1. Now I know that between 0 and 1, when x belongs to 0, 1, then fraction part of x is simply x. So I'll write a minus 2x square plus 2x plus a square is equal to 0. So this equation should have exactly one solution in the interval 0 to 1. So whereas a quadratic expression has exactly one root in any given two values, so the condition is f0 into f1, it should be less than 0. So that is, one of the values should be positive and the other value should be negative. So that is, the graph should intersect x-axis either here like this or like this. So one value is positive and the other value is negative. So f0 into f1 should be less than 0. If I write f0, what is f0? f0 is simply a square. And what is f1? f1 is a minus 2 plus 2 plus a square should be less than 0. So 2 and 2 will cancel. I'll take a common. So there will be a cube into 1 plus a should be less than 0. So the values will be minus 1 and 0. So there will be plus, minus and plus. So I need minus. So answer to this question will be the value of a should lie between minus 1 and 0. So now the question is, function fx is given as 1 upon greatest linear function of mod of x minus 1 plus greater function of mod of 12 minus x minus 11, and I need to find the domain of this function. So the only restriction that I see in this question is denominator should not be 0. So I need to solve this equation, which is greater function of mod of x minus 1 plus greater function of 12 minus x and minus 11, and it should not be equal to 0. Now what I'll do is I'll take three separate cases. Case 1, when x is less than 1. Case 2, when x lies between 1 and 12, and the third case when x is greater than 12. Now for the first case, when x is less than 1, so I know that this x minus 1, its value changes at 1, so this is plus and this is minus. And for the next one, 12 minus x, so this is minus and this is plus. So first expression will be negative, so it will be minus x plus 1, and then it will be 12 minus x will be positive, so there will be 12 minus x, and then minus 11, and it should not be 0. So I can write it as get a function of minus x plus 1 and plus 12 plus greatest in the function of minus x and then minus 11, it should not be 0. So 2 times greatest in the function of minus x and then plus 2 should not be equal to 0. So that is greatest in the function of minus x should not be minus 1. So get a function of x. So minus x should not be minus 1 simply means minus x should not belong to minus 1 comma 0. If I'll multiply with minus, I'll get x should not lie between 0 and 1. So the value of x should not lie between 0 and 1. Now what about the second case? Now in the second case, both of them they are positive. So I'll write greater is a function of x minus 1 plus greater function of 12 minus x minus 11 is unequal to 0. So here I'll get greater function of x minus 1 plus 12 plus greater function of minus x minus 11 is unequal to 0. So here 11 and 11 will cancel. So I'll get greatest in the function of x plus greater function of minus x should not be equal to 0. So I know that greater function of x plus greater function of minus x is 0 when x is an integer, and here it is non-zero when x is not an integer. So that means here it should be the value of x should not be an integer. So from the first case, I'll get x should be less than 1 but should not lie between 0 and 1. So from here I can say the value of x is simply less than or equal to 0. Here I'll get all the values of x between 1 and 12 except all the integral values, that is 1, 2, 3, 4 up to 12. And for the third case, when x is greater than 12, so this is positive and this is negative. So I'll write x minus 1 plus x minus 12 and minus 11 should not be equal to 0. So I can write 2 times greater function of x. So minus 1 minus 12 minus 13. So minus 13 and minus 11. So there will be minus 24. So there will be minus 24. Greatest in the function of x should not be equals to 12. So that is x should not belong to 12 to 13. So here x should be greater than 12 but should not be equal to 12 and 13. So the result I'll get is the value of x should lie between 13 to infinite. So answer to this question is either the value of x is less than 0, x belongs to minus infinite to 0, 0 included, union 1 to 12 except z, union 13 to infinite. So that is the answer to this question. Discuss the continuity and differentiability of the function fx equals greatest integral function of x sin pi x when the value of x lies between minus 1 and 1. So what I'll do is I'll draw the graph of y equals sin pi x. So I'll draw the graph of sin x. Now for sin pi x, I'll divide every value with pi. So now here it will be minus 1, 0, and this one will be plus 1. So I'll take two separate cases. Case 1, when the value of x lies minus 1 and 0. When x lies between minus 1 and 0, in that case, the value of sin x will also lie between minus 1 and 0. So here I can say the value of sin pi x will also lie between minus 1 and 0. Now if I'll multiply them, then when I'm multiplying two negative numbers, I'm bound to get a positive number. And because numerically their value lies between 0 and 1, so still their product will also lie between 0 and 1. So this value will lie between 0 and 1. So if I'll take their greatest integral function, so I'll write x sin pi x, this value will always be 0. So when x lies between -1 and 0, the value of greatest linear function of x sin pi x is 0. Now I'll take the second case. Now second case, when the value of x lies between 0 and 1. So when x lies between 0 and 1, the value of sin pi x, it will also lie between 0 and 1. So it will lie between 0 and 1. Now if I'll multiply it, I'll get this value as x sin pi x will always be greater than or equal to 0 but less than 1. It will be less than 1 because in order to achieve the value 1, for both of them, they have to be 1 simultaneously. But they are not 1 simultaneously at one point. So this value will always be less than 1. So in this case also, greatest linear function of x sin pi x is 0. So the given function fx in the interval -1 to 1 is nothing but a constant function which is 0. And any constant function in an open interval is both continuous as well as differentiable. So answer is, this function is continuous and differentiable in -1 to +1. Now the question is, solve the integral from 0 to pi greatest linear function of cot x dx. So I'll need to solve this question. So I'll use the property of definite integrals, and which is integral of 0 to a fx is same as 0 to a fa minus x. So I'll replace x with pi minus x. So I'll write 0 to pi greatest linear function of cot pi minus x into dx. Now cot pi minus theta is minus cot theta. So I can write it as from 0 to pi, and this is minus cot x into dx. Now I'll add the two integrals. So if I'll add them, I'll get 2i, and this is equals to 0 to pi. This is greatest linear function of cot x plus greatest linear function of minus cot x into dx. Now we know that greatest linear function of x plus greatest linear function of minus x, this is 0 when x is an integer, and this is -1 when x is not an integer. So if cot x is not an integer, then simply I can write 2i equals 0 to pi greatest integer function of x plus greatest integer function of minus x. It will be -1, so it will be -1 into dx. So there will be minus pi. So in this case, answer to this question will be minus pi by 2. Here the question is, find the number of solutions of the equation sin x is equal to greatest linear function of x. Now we know that greatest linear function, it's an integer. So that means sin x should also be an integer. So now in this case, sin x can only have 3 integral values. Either the value of sin x, it can be -1, or the value of sin x, it can be 0, or the value of sin x, it can be +1. Now, when the value of sin x is 1, the value of x is minus pi by 2, which is minus 1.54. And if I take greatest linear function of x is also -1, then I know the value of x should lie between -1 and 0. Now, minus 1.54, it doesn't lie in this interval. So there is no simultaneous solution to this case. So I won't get any solution from this. Now for the second case, when sin x is 0, then x is simply n pi, and one of the value will be x equals to 0. Now if I'll take greatest linear function of x is also 0, so then the value of x should lie between 0 and 1. So here we have a simultaneous solution at x equal to 0. So from here, one of the value that I'll get is the value of x, it should be 0. Now the third case is when the value of sin x is 1. When sin x is 1, then x is pi by 2, which is 1.54. And here, greatest linear function of x, it should be 1. So that is the value of x should lie between 1 and 2. Now 1.54, it does lie in this interval. So another solution to this equation is when the value of x is pi by 2. So there are two solutions to this equation. So number of solutions of this equation is simply 2. Another way of solving the same question can be using graphs. So I'll draw the graph of sin x. If I'll draw the greatest needed function, so it'll be this one. Then it'll be here. So these two graphs, they intersect at these 2 points. So one of the point is x equal to 0 and the other point is x equals to pi by 2. So from graph also we can say the number of solution to this equation is simply 2. Now the question is number of simultaneous solution of the equation y equals 1 by 3 greatest needed function of sin x plus greater function of sin x plus greater function of sin x. Now what I know is x plus n is simply greatest needed function of x plus n. So I can write it as y equals 1 by 3 greatest needed function of sin x, and this is greatest needed function of sin x plus greatest needed function of sin x. Now this is 2 sin x, which again is an integer. So again I can write it as 1 by 3 and it is greatest needed function of sin x plus 2 times greatest needed function of sin x. So here 3 and 3 will cancel. So this equation is simply y is the greatest needed function of sin x. Now we need simultaneous solution of the equation. So from here I can simply say this y, it is an integer. So when I look at this y plus greatest needed function of y equals 2 cos x, I know that I can write it as greatest needed function of y and then plus greatest needed function of y, and this is equals to 2 cos x. So that is greatest needed function of y is equal to cos x. Now because y is an integer, the value of cos x should also be an integer. So from here I can say greatest needed function of sin x should be equals to cos x when cos x is an integer. Now what are the integral values of cos x? So integral values of cos x are -1, 0 and +1. But the problem here is at the points where the value of cos x is -1, the value of sin x will be 0. So in that case, this greatest needed function will be 0. At +1 also, again sin x will be 0. And when cos x is 0, at those points, sin x will be plus or -1. So simultaneously, they cannot hold the same value. So in this case, there will be no solution to this equation. So there is no simultaneous solution of the two given equations. So number of simultaneous solution of this equation is simply 0. Now here the question is solve the equation greatest needed function of 2 cos x plus greater function of sin x is equal to -3. Now what I know is the value of 2 cos x will lie between -2 and +2, and the value of sin x will lie between -1 and +1. So in order to get this 2 cos x plus sin x as -3, the only way it is possible is when the value of greater function of 2 cos x is -2 and when the value of sin x it is -1. So that means greatest needed function of 2 cos x, it should be -2, and greatest needed function of sin x, it should be -1. That is the value of 2 cos x should lie between minus 2 and minus 1. So if I'll divide by 2, I'll get minus 1 cos x is less than minus 1 by 2. And for sin x, I'll get this value should lie between minus 1 and 0. Now, I'll need to find simultaneous solution of this equation. So when the value of cos x lies between minus 1 and minus half, and when the value of sin x lies between minus 1 and 0. So what I'll do is, I'll draw both the graphs. So I'll draw the graph of cos x. Now because both the functions, they are periodic with period 2 pi, so I'll take up a 2 pi interval and then I'll draw both the graphs. This is 1, this is minus 1, this is pi by 2, it is pi, and this is 3 pi by 2 and it is 2 pi. So that is the graph of y equals cos x, and I'll need to find a region where the value of cos x lies between minus 1 and minus 1 by 2. So I need to find where it lies between minus 1 and minus 1 by 2. So these points, so they'll be, now cos x is 1 by 2 at pi by 3, and this is pi plus pi by 3, so there'll be 4 pi by 3. So that is, the value of cos x will lie between minus 1 and minus 1 by 2 when the value of x lies between two pi by 3 and 4 pi by 3. Now what about sin x? So I'll draw the graph of sin x. The value of sin x will lie between minus 1 and 0 when the value of x lies between pi and 2 pi. So now I need to take the intersection of these two conditions. So if I'll take the intersection of these two conditions, then I'll get the value of x as the value of x should be greater than pi but less than 4 pi by 3. So answer to this question is simply the value of x should lie between pi and 4 pi by 3. The question is, let there is a function which is defined from R to R and it is given as greatest near function of x when x is less than or equal to 2 and 0 when x is greater than 2, where box x represents greatest near function, and if I is from minus 1 to 2, x fx square upon 2 fx plus 1 dx, then find the value of 4i minus 1. So in this case, I'll need to find out what is fx square. So if I'll put x square in place of x, so I'll get greatest new function of x square when x square is less than or equal to 2, 0, when x square is greater than 2. So which simply means it is greatest near function of x square when mod x is less than root 2. That is when x lies between minus root 2 and plus root 2, and it is 0 when either x is less than minus root 2 or when x is greater than plus root 2. Now I can further write it as when x lies between minus root 2 and minus 1, or when it lies between 1 and root 2. So in that case, the value of x square will lie between 1 and 2. Its greatest near function will be simply 1. Now when x lies between minus 1 and plus 1, in this case, the value of x square will lie between 0 and 1. So in that case, the greatest near function of x square will be 0, and also when x is less than minus root 2 or when x is greater than plus root 2, in that case also the value of this function is 0. So this function, its value will be 1 when the value of x lies between minus root 2 and minus 1, or when it lies between 1 and root 2, and then the value of this greatest real function will be 0 either when x lies between minus 1 and plus 1, or when x is less than minus root 2 or x is greater than plus root 2. Now we'll take another function which is fx plus 1. So if I write fx plus 1, then fx plus 1 simply will be greatest needed function of x plus 1 when x plus 1 is less than equal to 0, is less than equal to 2, and 0 when x plus 1 is greater than 2. So I can simply write it as, now greatest needed function of x plus n is greatest needed function of x plus n. So when x is less than equal to 1, and this is 0 when x is greater than 1. Now we'll come to this integral part. So the integral is given as minus 1 to 2 x fx square into dx upon 2 plus f x plus 1. Now I know that this fx square, it is 0 when x lies between minus 1 and plus 1, and it is 1 when x lies between 1 and root 2, and again when x is greater than root 2, this again will be 0. So I'll split this question in 3 parts. So I'll write it as minus 1 to plus 1. So in that case, the value of fx square, it is nothing but 0. So if it is 0, then this is simply 0 dx. Now plus, now between 1 and root 2, so now in this case, when x lies between 1 and root 2, the value of fx square is simply 1. So then it will be x and fx square, this value will be simply 1 upon, and this is 2 plus. Now when x is greater than 1, this value is 0. So this function in this interval will be simply 0. So there will be 0 into dx, and then plus the next one will be again from root 2 to 2. Now when x is greater than root 2, in that case also the value of greater function of x square or fx square is simply 0. So here also this is 0 dx. So the value of this integral is simply from 1 to root 2 x dx upon 2. So if I'll integrate, I'll get it as I equals 1 by 2 x square upon 2 from 1 to root 2. So this is 1 by 4, and here will be 2 minus 1, which is 1 by 4. So if I'll cross multiply, I can write 4i is equal to 1. That is the value of 4i minus 1 will be simply 0. Now this third question is, if fx is a polynomial function such that f alpha square plus f dash alpha square equals 0. Now assuming that it is a polynomial function with real coefficients, from here we can say f alpha must be 0 and f dash alpha must also be 0. We need to find this limit, which is limit x tends to alpha fx upon f dash x greatest integral function of f dash x upon fx. Now we know that any greater function of x is always less than or equal to x, and it is strictly greater than x minus 1. So from here we can say this greatest integral function of f dash x upon fx will always be less than equal to f dash x upon fx, and will be strictly greater than f dash x upon fx minus 1. Now we need to multiply it with fx upon f dash x. So if we multiply everything with fx upon f dash x, we can write this as fx upon f dash x into f dash x upon fx minus 1. It is less than fx upon f dash x into greater function of f dash x upon fx and less than equal to fx upon f dash x into f dash x upon fx. Now I'll cancel. Here this first part will cancel. So we'll get this as 1 minus fx upon f dash x is less than fx upon f dash x into greatest integral function of f dash x upon fx, that is less than or equal to 1. Now if we take this limit x tends to alpha, then we can write this limit x tends to alpha. Here also it will be this limit x tends to alpha, and here also it will be this limit x tends to alpha. So value of this limit on the right hand side, it is 1. We need to find value of this limit on the left hand side. Now this is 1 minus. Now what about this fx upon f dash x? Now if we know that f alpha is 0 and f dash alpha is 0, it means this alpha is double root of this function fx. So we can write this function fx as sum x minus alpha square into, and this f dash x will be sum x minus alpha into hx. So this fx upon f dash x will have x minus alpha and then some ratio of polynomials px upon qx. Now if we take this limit x tends to alpha, here alpha minus alpha will be 0. So value of this limit is 0. So this expression will take the limiting value 0. So limit on the left hand side is also 1. Now limit on the right hand side is 1. Limit on the left hand side is also 1. Then from sandwich theorem we can say that this limit will be equal to 1. So answer to this limit is 1, and that's your option B. And finally we have this question. We need to find this integral from 0 to 10 greatest integral function of under root 10x upon x plus 1 dx. Now let us take this as a function y, which is under root of 10x upon x plus 1. Now in order to solve this integral, what we'll do is we'll draw the graph of this function, and we'll draw it using transformation of greatest integral function. Before that, I'll differentiate this function. We'll find y dash. So it'll be 1 by 2 under root of 10x upon x plus 1 into 10, and here will be 1 upon x plus 1 whole square. So it will be greater than 0. So this function, it is strictly increasing function. So between 0 to 10, this function will be an increasing function. Now at 0, this value will be 0, and at 10, this value will be 10 by under root 11, and that is 3 point something. So if we draw this graph, so it will be some increasing function from 0 to 10. Now at 10, this value is 3 point something. Now we know for transformation of greatest integral function of x, we have to draw horizontal lines at integer points. So we have integer point at 1, at 2, and integer point at 3. So this is 1, 2, and 3. Now first we'll find these point of intersections. Now this point is when the value of this function is 1. So if we take this as 1, we'll get 10x upon x plus 1 will be equal to 1. So value of x here is 1 by 9. So this point is 1 by 9. Now for this, we'll put under root 10x upon x plus 1 equals to, now we square it, we'll get 10x equals 4x plus 4, or the value of x is 2 by 3. So this point will be 2 by 3, and then if we put it equals to 3, we'll get 10x upon x plus 1 will be 9. So we'll get value of x as 9. So this point will be 9. Now we know that in between any two lines, this greatest integral function, it comes to this bottom line. So here it'll be this 0. Here it'll be this value 1. Here it'll take the value 2. And in between 9 and 10, it'll take the value 3. Now this integral, it is nothing but it is this area. So value of this integral will be 1 into 2 by 3 minus 1 by 9 plus 2 into 9 minus 2 by 3 and plus 3 into 10 minus 9, which is 1, and this is 5 by 9 plus 18 minus 12 by 9 plus 3, 182 by 9. Now we need to find the value of 9i. The value of 9i is 182. So answer to this question is 182. Now question number 18 is, we need to find number of real solution of this equation, which is mod of 2x minus greatest interior function of x, it is equal to 4. So we can write this as 2x minus greatest interior function of x, and it is equal to plus or minus 4. Now we'll take this first case. When it is plus 4, we'll get 2x minus greatest interior function of x, and it is equal to plus 4. We can write x as greatest interior function of x plus fraction part of x. So it will be 2 times fraction part of x minus greatest interior function of x, it is equal to 4. So from here we'll get fractional part of x as 4 minus greatest interior function of x divided by 2. Now we know that fractional part function, it always lie between 0 and 1. So we'll write 0, and this is 4 minus greatest interior function of x upon 2, and it lies between 0 and 1, so it will be 0, and then 4 minus greatest interior function of x is less than 2. We'll get minus 4, and then greatest interior function of x minus 2. So greatest interior function of x should be greater than 2 but less than equal to 4. So greatest interior function, it can only take integral values. So the only integral value possible in this case is either this value is 3 or greatest interior function of x is 4. Now we'll take greatest interior function of x as 3, then we'll get fraction part of x as 1 by 2. And in this case, value of x is 3 plus 1 by 2. That should be 7 by 2. And if greater function of x is 4, fraction part of x is 0. Here, the value of x is simply 4. Now we'll consider the second case. Now here again, we can write 2 times greatest interior function of x plus 2 times fraction part of x minus greatest interior function of x is equal to minus 4. We'll get 2 times fraction part of x as minus greatest interior function of x plus 4. Now again, it'll lie between 0 and 1, so it'll be 0, and then minus greatest interior function of x plus 4 divided by 2, and it should be less than 1. So we can write minus 2 is less than greatest interior function of x plus 4 is less than equal to 0. So here we'll get minus 6 is less than greatest interior function of x is less than minus 4. So here the two values of greatest interior function x possible are minus 4 and minus 5. So we'll get 2 solutions here and 2 solutions here. So total number of solutions to this equation is 4, and that's your option number A. Now here the question is, find x satisfying this equation, greatest interior function of tan inverse of x plus greatest interior function of cot inverse of x equals to 2. Now we know that range of tan inverse of x is minus pi by 2 to plus pi by 2, and a range of cot inverse of x is from 0 to pi. So the possible values of greatest interior function of tan inverse of x, they are minus 2, minus 1, 0 and 1. So we have 4 values, and greatest interior function value of cot inverse of x, it will be 0, 1, 2 and 3. So we have 4 possible values for greatest interior function of cot inverse of x also. Now we need their sum to be 2. Now this sum, it can be 2 when case 1, when greatest interior function of cot inverse x, it is 3, and greatest interior function of tan inverse x is minus 1. Second case, when greatest interior function of cot inverse x is 1, and greatest interior function of tan inverse x is also 1. And then finally, this third case, when greatest interior function of cot inverse x is 2, and greatest interior function of tan inverse x is 0. Now we need to find simultaneous solutions for these conditions. Now cot inverse x equals 3 means the value of cot inverse, it should lie between 3 and 4. Now cot inverse, it is a decreasing function. So we'll take cot, then sine will decrease. So we'll get cot 3 is greater than equal to x is greater than cot 4. And here, when the value of tan inverse x is minus 1, that means value of tan inverse of x, it should lie between minus 1 and 0. If we'll take 10, so we'll get minus tan 1 is less than equal to x is less than 0. Now we'll need to find simultaneous solution of these two conditions. And for that, we'll need to compare the values of cot 3 and minus tan 1. And what we'll do is, we'll draw the graph of tan inverse of x and we'll draw the graph of cot inverse of x. So for tan inverse, we have asymptotes at minus pi by 2 and plus pi by 2. That is the graph of tan inverse of x. So this is minus pi by 2 and this is plus pi by 2. And then for the graph of cot inverse, we have asymptotes at 0 and pi. Now these two graphs, they'll intersect at 1 and this value is pi by 4. Now if we'll draw a line at 3, this point is cot 3, and if we'll draw a line at minus 1, this point is minus tan 1. So clearly cot 3 is less than minus tan 1. So this first interval is from cot 4 to cot 3 and this second interval is from tan 1 to 0. So there is nothing common between the two intervals. So in the first case, there is no simultaneous solution. Now for the second case, when cot inverse of x is equal to 1 and tan inverse of x equals 1. So in this case, cot inverse, it will lie between 1 and 2 and tan inverse will also lie between 1 and 2. Now here, if we'll take cot, so we'll get cot 1 is greater than equal to x is greater than cot 2 and here tan 1 is less than equal to x is less than tan 2. Now we'll need to compare the values of tan 1 and cot 1. Now we'll draw a line at 1. Here we'll get tan 1 and just before this one we'll get cot 1. So value of cot 1 is less than value of tan 1. So this first interval is from cot 2 to cot 1 and the second interval is from tan 1 to tan 2. There is nothing common again between the two intervals. So for this second case also we'll get no solution. Now we'll come to this third and final case when the value of cot inverse of x lies between 2 and 3 and the value of tan inverse of x lies between 0 and 1. Now in this case, we'll get this as cot 2 is greater than x is greater than cot 3 and here we'll get this as 0 is less than x is less than tan 1. So we already have tan 1. Now we'll need to figure out cot 2. Now we'll take cot 2. Now 2 will be greater than pi by 2. So cot 2, it will again be less than 0. So in this interval again, we are having values in the negative x and the second interval is between 0 and tan 1, which is on the positive side. So again, we do not have any common value between the two intervals. So here again, we have no solution. So this equation, greatest integral function of tan inverse x plus greatest function of cot inverse x equals 2, it doesn't have any solution. So answer to this question is no solution. Now question number 18, it says let P and B number of digits when 8 to the power n is written in base 6 and let Q and B number of digits when 6 to the power n is written in base 4. We'll need to find this limit, which is limit n tends to infinite Pn Qn upon n square. Now there is a direct formula for that. So if we write 8 to the power n to the base of 6, then number of digits Pn, it is given by greatest integer function of log 8 to the power n to the base 6 and then plus 1. So this is the formula to find out number of digits in other base. So in the same way, we can find number of digits Qn when the base is 4. So Qn will be log base is 4 and number here is 6 to the power n and plus 1. So basically Pn is n log 8 base 6 plus 1 and Qn is greatest integer n log 6 base 4 plus 1. Now we need to find this limit, which is limit n tends to infinite Pn into Qn upon n square. Now in greatest integer function, we know this property that greatest integer function of x is always less than or equal to x and it is greater than x minus 1. So I can write Pn is less than or equal to n log 8 base 6 plus 1 and it is greater than n log 8 base 6. In the same way, we can write Qn. So Qn will be less than n log 6 base 4 plus 1 and here will be n log 6 base 4. Now if we multiply them, then we can write it as n square log 8 base 6 into log 6 base 4 is less than Pn into Qn and it is less than n log 8 base 6 plus 1 into n log 6 base 4 plus 1. So now I'll need to find this limit. So I'll need to divide it with n square. So I'll also divide it with n square. So if I'll divide it with n square and I'll take this limit also. I'll take this limit n tends to infinite. Now since it is an infinite limit, so highest power of n in the numerator and denominator is 2. So answer to this left hand limit will be simply log 8 into log 6 and here it is limit n tends to infinite Pn Qn by n square, and here also the highest power is n square. So here also this limit will be log 8 base 6 into log 6 base 4. Now Sandwich theorem says if fx lies between gx and hx and if limiting value of gx is L and limiting value of hx is L, then the limiting value of this limit is also L. So which simply means the value of this limit is equal to log 8 base 6 into log 6 base 4. So I can write it as log 2 base 8 upon log 6 base 2 and here will be log 6 base 2 upon log 4 base 2. So it will cancel. So 8 is 2 cube and 4 is 2 square. So the value of this limit is simply 3 by 2 and that's your option number C. So let us take up a question, and the question is find the value of root 3 plus root 2 plus 1 to the power 6 plus root 3 plus root 2 minus 1 to the power 6 plus root 3 minus root 2 plus 1 to the power 6 plus minus root 3 plus root 2 plus 1 to the power 6 and the fractional part of this entire value or number. So where these brackets, they represent fractional part function. Now we need to find the fractional part of this given number. Now what I'll do is I'll write this as root 3 plus root 2 and then plus 1 to the power 6, and here I'll write root 3 plus root 2 minus 1 to the power 6. Here it is root 3 minus root 2 plus 1 to the power 6, and here I'll take minus 1 common. So minus 1 to the power 6 will be simply plus 1. So I'm going to write it as root 3 minus root 2 and minus 1 to the power 6. Now if I write the series summation for this one, so using binomial, so I'll consider this as A and this as B. So I can write the series as summation r varies from 0 to 6, NCR root 3 plus root 2 to the power 6 minus r, and then 1 to the power r will be same 1. So here r varies from 0 to 6, and here will be 6CR, it will be root 3 plus root 2 to the power 6 minus r, and then minus 1 to the power r. In the same way, I'll write it for this one. So it will be summation r varies from 0 to 6, 6CR root 3 minus root 2 to the power 6 minus r, and for this one it will be summation r varies from 0 to 6, 6CR root 3 minus root 2, 6 minus r, and then minus 1 to the power r. Now if I look at these two terms, it is nothing but a plus b and a minus b. So what will happen is, when this r is an odd number, in that case these two terms they'll cancel, and when r is an even number, they'll add up, right? So what I'll do is I'll write it as 2 times and summation. Now r will take only even values, so r will be either 0, 2, 4 and 6. So I'll write it as 6CR root 3 plus root 2 to the power 6 minus r. So when the value of r is odd, these terms they'll cancel out, and when r is even, they're going to add up, right? In the same way I can write it for second one also. There'll be 2 times and summation. Again r will take even values 0, 2, 4 and 6, and here will be 6CR root 3 minus root 2 to the power 6 minus r. Now I'll take the two summations together. So I'll write it as 2 times and then summation r varies from 0 to 4 and 6, and I'll also take 6CR common. Then I'll write it as root 3 plus root 2 to the power 6 minus r plus root 3 minus root 2 to the power 6 minus r. When r is even, then 6 minus r will also be even, and this again is of the form a plus b and a minus b. So in this case again, all the even number terms they'll cancel. So here what I'll get is 2 times summation r varies from 0 to 4 and 6, and will be 6CR, and here I'll get 2 times. So I'll get this first term, which is 6CR 6 minus r C0 root 3 to the power 6 minus r root 2 to the power 0, and then plus 6C2 root 3 to the power 6 minus r minus 2 root 2 square, and this series will continue. Now when I look at this series, root 3 to the power 6 minus r is an even number, so 6 minus r is even, 6 minus r minus 2 is even, root 2 to the power 0 is even, power 2 is even, power 4 is even. So every time when I'm getting a square root, I'm getting it with an even power. So when I'm getting square roots with even power, I know there'll be no irrational terms in this expression. All the terms, they'll be simply integral. So that is the value of this number, or this number is actually an integer. Now when this number is an integer, and if I have to take the fractional part of any integer, so fractional part of any integer is simply 0. So answer to this question is 0.
So the question is, solve the inequality x square minus 4 is less than greatest integer function of x. Now what I'll do is, I'll draw the graph of y equals x square minus 4, and I'll draw the graph of y equals greatest integer function of x. So first I'll draw the graph of greatest integer function of x. And then I'll draw the graph of y equals x square minus 4. Now that is the graph of y equals x square minus 4. Now there are 2 points of intersections. For this point of intersection, I will write and this point of intersection is intersection of x square minus 4 and 2. So I'll get x as root 6. Now, in order to solve this inequality, I'll need to find the region where the graph of x square minus 4 lies below the graph of greatest integer function of x. So the graph of x square minus 4 lies below the graph of greatest integer function of x in this interval. So answer to this inequality is x belongs to minus under root 2 to under root 6.